quantum mechanics, for those of you who don't know, is this wonderfully successful theory that we developed mostly over the first quarter of the 20th century that's supposed to apply to everything in the universe, but really becomes manifest and necessary when we look at microscopic things, when we look at electrons or atoms or very, very small scale things. And we can use this theory to extraordinary precision. We can make predictions that have been tested to 12 decimal places of accuracy. Quantum mechanics is absolutely necessary to understand why the sun shines, or how transistors work, or why this table is solid, okay? So why does Feynman say this? Because even though we can use quantum mechanics to make predictions, if you ask physicists, but what's really happening, they don't know. And that's okay. It's okay not to know things, but when you don't know, what you should try to do is to learn, is to figure it out. And as a field, physics has decided not to do that. Rather than taking people who are trying to understand quantum mechanics at the deepest level and treat them as the superstars and most important people in the field, they push them out of the field. They've decided that trying to understand quantum mechanics at a deep level is not our job as physicists. It's only to make predictions. I think that this is bad. The analogy I like to use is with Aesop's fable of the fox and the grapes. If you remember this one, the fox sees the grapes and would like to eat these juicy, wonderful grapes and jumps up but can't reach the grapes. The fox is unable to get to the grapes. So the fox says, you know what? I never really wanted those grapes anyway. They were probably sour. The fox represents physicists, and the grapes represent understanding quantum mechanics. We used to try very hard to understand quantum mechanics, and we subsequently stopped, and I think that was a mistake. So let me tell you how we got to quantum mechanics. This is a fake version of the history, but it gives you an idea. So by 1909, we had this picture of the atom, which is the same cartoon you will always see when people talk about atoms. I think it's literally the logo of the Atomic Energy Commission, or the Nuclear Regulatory Commission. There's a nucleus at the middle of the atom, which we now know is full of protons and neutrons, and there are electrons orbiting around the atom, okay? The problem is that even though this is consistent with certain pieces of data, it can't be true as the final answer, at least according to the standards of classical Newtonian mechanics, because these electrons zooming around in orbits should be emitting electromagnetic waves. When you take a charged particle like an electron and you shake it in any way, it has an electric field radiating out in all directions. So when you move the electron, the field adjusts. And when you move it up and down, the field waves, and we see those. That's where the light that we're seeing right now comes from vibrating electrons. So these electrons that are moving around in circles should be emitting light, and that means they should be losing energy, and they should spiral into the nucleus of the atom. And you can calculate how quickly that should happen. It's about 10 to the minus 11 seconds, which is a very short period of time. So in other words, according to the rules of classical mechanics applied to the Rutherford model of the atom, all matter should be dramatically unstable. You and the chair you're sitting on and this table and the Earth itself should collapse into a point in a tiny fraction of a second. That prediction does not fit the data, so we need to do something better. There was many ideas batted around. What we eventually hit upon was, don't think of the electron as a point particle in an orbit. Think of the electron as a wave. In particular, we dubbed this the wave function, which is the most boring, uninspiring name for the most important thing in all of physics. The wave function is the idea that rather than being in an orbit around the nucleus of the atom, think of the electron as being described by a wave that is spread out around the atom. And just like a violin string that you pluck in different ways, a string that is tied down at both ends has the fundamental frequency that it can vibrate at, and then there are overtones, harmonics, that it can vibrate at in different ways. The point is that there's a discrete set of different ways it can vibrate. Likewise, if you think of the electron as a wave rather than as a particle, there's a discrete set of shapes that wave can have in the atom, and there's a minimum energy shape. So rather than just spiraling in to the center of the nucleus, the electron goes to its minimum energy configuration, which is still spread out. It's the shape in the upper left here, spherically symmetric. These other shapes are higher energy versions of the wave function of the electron. And then it just sits there forever. And if you remember high school chemistry, you were tortured by pictures of electrons doing these things and the various orbitals that they could be in. And so this became a way of thinking about why matter is stable. Even better, a couple of years later, Erwin Schrodinger came up with an equation for how these orbitals, electron wave functions, actually behave. And I give you the details of the Schrodinger equation because I know you all want to go off and solve it in your spare time. There are people here at Google who spend a lot of time solving this equation on quantum computers. And you don't need to know the details of the Schrodinger equation if you are not a quantum mechanical expert. What you need to know is that there is an equation. Okay, so physicists love equations for good reasons. It's because you can go from the original idea, the electron is a wave around the atom, and now you can just apply it widely. You can apply it to any other circumstance. You can take the wave function doing anything, and you can let it evolve. You can solve this equation. In words, the Schrodinger equation says any one wave can be decomposed into different energy parts, and every energy part evolves at a separate rate. So the energy of the wave is proportional to how fast it evolves. That's the Schrodinger equation. That's the entire thing. And so this equation still, suggested in 1926 is still right as far as anyone knows. It's one of the fundamental rules of nature. So you might think that we're like triumphant, that quantum mechanics is basically done, that we know that now electrons are not particles, they're waves. This is the equation they obey. That's what you want in a good physical theory, an understanding of what nature is and which equation it obeys. The problem is the data don't stop there. So this is a wonderful little image of a chunk of uranium in a cloud chamber. Okay, so a cloud chamber has some pressurized gas in it that when a charged particle moves through the gas, it ionizes the particles around it and it creates a little track. Okay, so if you have a chunk of uranium, it's radioactive, it will actually emit electrons and alpha particles and things like that. And you can use the Schrodinger equation to say, well, what does the wave function of the emitted electron look like? The answer is it looks like a spherical wave. The electron wave function comes out in all directions, more or less equally. There's details, but that's the basic story. But then you look at it, you never see an electron coming out in all directions equally. What you see in this picture are straight lines, trajectories, as if the electron is a particle again. What's up with that? We still have not answered this question, what's up with that? This is the sad part about the modern understanding of quantum mechanics. So what people said was, look, it looks like the way that electrons behave in their wave functions is different when you're not looking at them, like when they're in the nucleus, around the nucleus of an atom, versus when you are looking at them, like when they're in the bubble chamber or cloud chamber, okay? Now, surely that can't be the final answer, but what the strategy adopted by physicists in the 1920s is, yes, that's the final answer. So they invented an idea called the collapse of the wave function. They said, sure, wave functions for electrons or whatever, they obey the Schrodinger equation when you're not looking at them. But when you measure a quantum mechanical system, its wave function suddenly and unpredictably changes. And rather than predicting exactly what's going to be able to happen, you can predict the probability of different things happening. And the probability is largest where the wave function was largest. And after the measurement has occurred, the wave function changes to be localized where you observed it. So on the left here, you have a picture of a wave function that might be all spread out for an electron. You imagine measuring the position of the electron. Its wave function collapses somewhere. And if you looked at it again right away, you would see it in the same place. So this is the attempt to understand why electrons are all spread out in wave functions when you're not looking at them, but look like particles when you do look at them, because the act of measurement is something special. It really does something to the particle in a particular way. So this is what's called the textbook or Copenhagen interpretation of quantum mechanics. This is what we teach our undergraduates. I'm not like going to reveal the truth. This is what we actually tell our kids. This is what I was told. The rules of quantum mechanics, according to this way of thinking, come in two groups. There's one set of rules for when you're not observing the system. Those rules say that the electron is described by wave functions, or whatever quantum system, there's a wave function, and that wave function obeys the Schrodinger equation. And that's exactly in parallel with the rules of classical mechanics. In classical mechanics, there's a system, and it obeys some equations, and that's it. Those are all the rules. In quantum mechanics, you have those rules, but then there's extra rules for what happens when you measure or look at or observe the system. You can only measure certain things. When you do, the wave function collapses, and the best you can do is to predict the probability of a certain collapse. That's the Copenhagen interpretation. This is clearly unacceptable as a fundamental theory of nature. I mean, what are you talking about? It's fine for making predictions and building things, but it's clearly not the final answer. This was the point of contention in the famous Bohr-Einstein debates in the 20s and 30s. Niels Bohr was a founder and defender of the Copenhagen interpretation. Einstein said, look, that's fine as far as it goes, but clearly it has not gone far enough. We need to look harder. This is why the title of my book is Something Deeply Hidden. There's something else going on that we haven't yet explicated. And Bohr and his friends said, no, it's fine. Don't worry about it. And Bohr and his friends totally won the public relations battle, but I think that Einstein was actually right in this particular dispute. So let me just mention two reasons why the Copenhagen interpretation by itself can't be the right final answer. There's what we might call the reality problem. We started by saying that electrons should be thought of as wave functions, but what is the wave function really? Is the wave function a complete description of nature? In other words, is there an isomorphism between the mathematical formalism of a wave function and what reality is doing? Or is it part of nature, but not the whole part? Maybe there's other variables there. That's what Einstein himself thought. He thought that there was a wave function, but there were also particles. So the wave function described what happened when you weren't looking at them, but when you measure the thing, you see the actual particle. And in the modern version, these are called hidden variable theories. Bohmian mechanics is the most famous version. But maybe the wave function doesn't represent reality in any way. There's other people who say, just use the wave function to make predictions. Don't think of it as part of reality. So the fact is that even professional physicists who use quantum mechanics every day can't tell you what it says about reality. And if you ask them, they will tell you in all honesty, bless their hearts, that they don't care about reality. All they care about is making predictions for observations. I think that's a bad attitude to have, but I'm in a minority there. The other problem is called the measurement problem. And this one is even more obvious as a problem. What do you mean, make a measurement or look at something? Like what counts as a measurement? Who is able to do measurements? Is it just people? Do you need to be human? Do you need to be conscious? What about when you're asleep? Can cats make measurements? What about video cameras? What if I don't look at it very closely? What if I glance at it? Does that count as a measurement? How fast does it happen? When does it happen? A well-defined, rigorous theory of physics should answer all of these questions, and the Copenhagen interpretation doesn't answer any of them. It just says, don't worry about that. You know a measurement when you see it. I think that's not quite good enough to be a fundamental theory of nature. So there are different alternatives. These days, this is all put together in the 1920s, right? These days, we actually have perfectly well-defined theoretical physics frameworks that do answer these questions. The problem is we have more than one, and we're having trouble deciding between them. So I am not going to be in any sense fair in this talk. I'm just going to tell you my favorite one and let you know there are others. Buy the book if you want to see the others. Okay. Here's my favorite. It came from Hugh Everett, who was a graduate student and was incredibly criticized for his ideas and left the field right away. And so Hugh Everett says the following. He says, here's the solution to all of your quantum problems. Chill out. Stop working so hard. You're trying too hard with all of this stuff. You've made up a whole separate set of rules about quantum mechanics for what happens when you measure or observe a system. Just erase all those rules. Just forget about them. You want to know what reality is? It's the wave function. You want to know what wave functions do? They obey the Schrodinger equation. And that's it. That's all you need to know. So in other words, this is the Everett interpretation of quantum mechanics. There's only one set of rules. They are always obeyed, and all it says is they're wave functions obeying the Schrodinger equation. Now, there's a problem with this interpretation, which is why it was not invented by Bohr or Einstein in the 1930s, in that it doesn't seem to quite map onto our experience, right? Like we saw the cloud chamber with all the little particles moving. They don't look like they're obeying Schrodinger's equation. So what's going on? And Everett says there are two things that you've forgotten about that are already built into quantum mechanics. He doesn't add anything, right? He erased some rules. He says there are two things that are already there in quantum mechanics that if you just take them seriously, everything will be fine. One thing is you yourself are a quantum system, right? You are part of the wave function of the universe. You are not a classical system. In Copenhagen, depending on who was talking and what time of day it was, they would admit that they treated the observer as classical. There's even something called the Heisenberg cut, advocated by Werner Heisenberg, that separates the classical macroscopic world of observers from the microscopic quantum world. And Everett says, look, you might be big and made of a lot of atoms, but the atoms you're made of obey the rules of quantum mechanics. So you do too. Treat yourself as quantum mechanical. And the other point that he wanted to emphasize was entanglement. Again, a feature of quantum mechanics, not anything that he added to the theory. So let me mention what entanglement says. My favorite example is the Higgs boson, because I wrote a book about that, okay? The Higgs boson we discovered back in 2012, and the reason it's my favorite example is because the Higgs boson is a spinless particle. Every elementary particle comes with a quantity called spin, which is really just like the spin of the Earth or a spinning top or anything like that, except when you get down to that microscopic realm, spin comes in definite quantized values. So the spin of the Higgs boson is exactly 0. The spin of an electron is 1/2. Which means that if you observe the spin of an electron in quantum mechanics, it'll either be spinning clockwise by an amount 1/2 or spinning counterclockwise by an amount 1/2. And we call these spin up and spin down. So we know from the observations and from the theory, the Higgs boson can decay into 2 electrons. Technically, an electron and an anti-electron, a positron, so the charge is conserved, but let's ignore that complication. So one particle with 0 spin is decaying into 2 particles with spin 1/2. But spin is conserved. Spin is angular momentum. It's part of that, right? So it must be that when the Higgs boson decays into an electron and an anti-electron, they're each spinning, but they better be spinning in opposite directions. The total spin has to add up to 0 because that's what it was for the Higgs boson all by itself. Now, we don't know which way it is, right? Like one electron is spin down and the other one is spin up, but we don't know which is up and which is down. So if you go through the Schrodinger equation, what you find is that it's not one or the other. It's a superposition of both. One of the crucial features of quantum mechanics is that you have different pieces of the universe, but unlike in classical mechanics, the different pieces don't have their own individual states that we can talk about. Rather, there's only one quantum state. There's only one wave function of the entire universe. So when you talk about what the 2 electrons are doing, you need to talk about both of them at once. So you know that electron 1 might be spin up or might be spin down. There's a 50-50 chance. You know that electron 2 might be spin up or spin down. There's a 50-50 chance. But you also know that they're not spinning the same way. So if you measure the spin of electron 1 and find that it's spinning up, you instantly know that electron 2 is spinning down. And the state of the Higgs boson decaying into something is that it decays into a superposition of spin up for electron 1, spin down for electron 2, plus spin down for electron 1, spin up for electron 2. That's entanglement. What is happening to particle 1 is entangled with what's happening to particle 2. They're not independent from each other. This is so important. Let me say exactly the same thing again in slightly different words to drive it home. There's only one wave function, the wave function of the universe, what Everett called the Universal Wavefunction. His first title for his thesis was The Theory of the Universal Wavefunction, but his advisor did not let him get away with that. So the lesson is you might think that if you have 2 electrons and you don't know the spin of either one, but you know they can be in superpositions, you might say, well, electron 1 is in a superposition of up and down, electron 2 is in a superposition of up and down. Quantum mechanics says there's not 2 separate wave functions for the 2 electrons, there's only one. And they are entangled in the following way. And this was actually invented, or at least appreciated, by Einstein. Einstein and Schrodinger wrote letters back and forth because despite playing fundamental roles in the origin of quantum mechanics, neither Einstein nor Schrodinger liked how quantum mechanics was going. They didn't like the Copenhagen interpretation. And so the origin of entanglement was in Einstein's effort to show that quantum mechanics couldn't be complete as yet, because you can send one of these particles light years away from the other one. And if you measure the spin of one, you instantly know the spin of the other. And Einstein says, like, look, I'm Einstein. I know about this thing called relativity. You can't send information faster than the speed of light. How does it know? Way over there. And that's the spooky action at a distance that he invented. But it's there. It's true. It's part of quantum mechanics, and you can actually test it experimentally. So let me show you then how entanglement explains the measurement problem according to the Everett interpretation. And we're going to use Schrodinger's cat to explain this. You've probably heard of the thought experiment put forward by Erwin Schrodinger. He has a box. He puts the cat in the box, closes the box, and there's a little apparatus there that has a quantum wave function that has a probability of opening some vial and emitting gas into the box or not doing that. The gas Schrodinger decided to contemplate was cyanide. So the cat's either alive or dead. His daughter literally said later, I think my father just didn't like cats. There's no reason to kill the cat in the thought experiment. It plays no role. So in my version of the thought experiment, it's sleeping gas. And what happens is there's a quantum system that evolves into a superposition of having decayed or not. So there's a Geiger counter or some other detector that evolves into a superposition of having clicked or not. So the box and the gas evolve into a superposition of having been emitted or not. So the cat evolves into a superposition of being awake or being asleep. The whole mess is just designed to take a superposition of a tiny microscopic quantum system and amplify it to a macroscopic world. It doesn't matter that it's a cat. Honestly, the Geiger counter or the box by itself would have worked perfectly well. But remember, Schrodinger was unhappy about quantum mechanics. The point of the Schrodinger's cat experiment was not to go like, look how weird quantum mechanics is. Schrodinger said, what you're telling me, Mr. Bohr, is that when I opened the box, before I opened the box, the cat was in a superposition of awake or asleep. And after I open the box, it suddenly snaps into either awake or asleep. Surely you don't believe that, right? That was his point. And so in other words, if you knew about classical mechanics, it could be perfectly plausible to say there's a cat in the box, it might be awake, it might be asleep, but I don't know. But the only two possible states of the cat are it's awake or it's asleep. In quantum mechanics, we have a new possibility of this superposition, that the cat can be in a combination of awake and asleep. And then we tell a story about what happens when we open the box and measure that superposition. And that story is very different in Copenhagen versus in Everett. So in Copenhagen, we treat the observer as classical. So I'm putting classical things in square brackets and quantum things in parentheses. So the role of the observer here is played by Niels Bohr. And we start with a system where the cat is quantum and in a superposition, and Niels Bohr is classical, and he's not yet opened the box. He opens the box, and that's observation or measurement. And according to the Copenhagen interpretation, the wave function collapses. And after that measurement, either the cat was awake and the observer measured it to be awake, or the cat was asleep and the observer saw it sleeping. Those are the two possibilities, and there's a certain probability you can calculate. So Everett says, ignore all of this business about wave functions collapsing. Just obey the Schrodinger equation. Just ask what the Schrodinger equation would predict for this particular setup. So there's no collapse, and there's only one wave function, and the observer is quantum in their own right. So this is Hugh Everett now playing the role of the observer. So measurement in Everett's version of quantum mechanics is just obeying the laws of physics. It's just open the box and let Schrodinger equation do its work. And what happens inevitably, and everyone agrees on this, is that the wave function of the universe evolves to a superposition of the cat was awake and the observer saw the cat awake, and the cat was asleep and the observer saw the cat asleep. Again, if you obey the Schrodinger equation, that's what happens, no ifs, ands, or buts. The problem is, it looks like you, if you're the observer, would be in a superposition of having seen two different things. And nobody in the history of human beings has ever felt like they are in a superposition of having seen one thing or having seen another. So the immediate rejection of Everett's theory was because it doesn't fit the data. It doesn't explain our experience. It doesn't explain why we see tracks that look like particles in the cloud chamber. So miraculously, Everett got it right, despite the fact that in some sense he had no right to. The real explanation for this comes from decoherence, which is a process which really wasn't understood until the 1970s. Remember, I said that the point of quantum mechanics is there's only one wave function for the whole universe, not separate wave functions for separate pieces. And then I put into the wave function the cat and the observer. I really should put in the entire rest of the universe, right, to be strictly correct. So here's the entire rest of the universe. It's usually in this context called the environment. So I made a picture of grass. But really what you should think of is like the light coming from these light bulbs or the air in the room, like all the stuff, all the degrees of freedom that we're not explicitly keeping track of, that are bumping into us all the time, but we don't know, where every single individual photon is. So long before we open the box, in the box, there are photons, there are air molecules, etc. They will interact with the cat. And they will interact with the cat differently depending on whether the cat's awake or asleep, because the cat is in different locations in the box, right? So a photon will hit it or will not hit it depending on whether the cat is awake or asleep. So the environment becomes entangled with the cat long before you open the box. And then you finally open the box and you say what you're doing is called measurement, but really you're just becoming entangled with the two different quantum states that were always there. Now, why does it matter? It looks a lot like this equation at the bottom is very similar to the equation we had before. What matters is that these two different states of the environment, well, let me put it this way. The environment is doing two different separate things in the two parts of the wave function, the part where the cat's awake and the part where the cat's asleep. And the technical term is that these two environment states are orthogonal to each other. You can show mathematically this will happen very, very quickly. And what that means is that the separate two terms in this equation evolve separately. They obey their own equations of motion. If something happens in one part of that sum of two terms, it does not affect anything happening in the other term. So Everett says this is the prediction of the Schrodinger equation, and it's right. Believe it. This is the final answer. What you haven't realized is you're asking, why don't I feel like I am in a superposition? The answer is because there are now two of you. There is one of you that saw the cat awake and one of you that saw the cat asleep. It's as if these two different parts of the superposition describe different worlds. So the crucial part here is that Everett doesn't put the worlds in. The Everett interpretation, I'm not really revealing a surprise here, it's sometimes called the many worlds interpretation of quantum mechanics. He never called it that. The name was not invented until 1970 by Bryce DeWitt. The point is, if you just have the Schrodinger equation and you just follow it what it does, the worlds appear like it or not. They were always there. Everett just points out that they naturally come to be. The process of decoherence separates the wave function into distinct branches that no longer interact with each other, so they are, for all intents and purposes, separate worlds. Now, there's a bunch of questions you can ask about the many worlds interpretation. Some of them are easier to answer. Some of them are hard. Many of them are hard, to be honest, but I'm not going to dwell on all of them. I just want to give you a flavor for how we answer them. So one question is, how many worlds are there? We don't know. Is the short answer. We don't even know whether the number of worlds is finite or infinite, okay? The straightforward and simple answer is that there are infinitely many worlds. This is what Everett himself would have believed. At the technical level, for those of you who do know a little bit about quantum mechanics, the question is, what is the dimensionality of Hilbert space, the space of all the possible wave functions? For simple systems like an electron in non-relativistic quantum mechanics or a quantum field theory, Hilbert space is almost always infinite dimensional, and therefore, for all intents and purposes, there are an infinite number of worlds. But we don't know that for sure, and people like me think that quantum gravity implies that the Hilbert space is actually finite dimensional, so maybe there's only a finite number of worlds. But even if it's a finite number, it's a really, really big number. So rather than thinking of the branching of the wave function as happening at special events where you work hard to make it happen, it's happening all the time. there are radioactive decays in your body roughly 5,000 times a second, and every one of those duplicates the universe, okay? So rather than thinking of like bang, a special event that splits the universe, there's a constant whooshing as the universe is subdivided. And that's the way to think about it. It's not a duplication of the world with twice as much energy and everything. There's a certain amount of worldness in the equations, and it's being subdivided and differentiated as time goes on. Think of the world as splitting, not as being copied in some way. Now, there are some objections that I think I can easily answer. One is that there's just too many universes. Sorry, I don't like it. This is not a very scientifically respectable worry, but, I get it. The problem is that, there's enough stuff going on in one universe. Doesn't it seem like ontologically extravagant to add all this extra stuff in? The response to this is that once you believe quantum mechanics, the potential for all these worlds was always there. Once you believe that electrons can be in superpositions, you should believe that people can be in superpositions and worlds can be in superpositions. Hilbert space is the name we attach to the space of all possible wave functions. It's not any bigger in many worlds than it is in Copenhagen or anyone else's interpretation of quantum mechanics. It's just that many worlds lets the wave function be wherever it wants to be in Hilbert space. So this might be an objection to quantum mechanics, but it's not an objection to many worlds per se. The second question is, how can you test this theory? You're saying there's all these other worlds out there that I can't interact with. Doesn't that violate the spirit of science that I should be able to test my predictions? Well, there's a longer conversation here, but let's appeal to Karl Popper, the philosopher who said that a good scientific theory should be falsifiable. Of course, every scientific theory makes some predictions that you can't test. The question is, are there any experiments you could imagine doing that could give you answers that would cause you to reject the theory? And remember, all Everett is the statement there are wave functions and they obey the Schrodinger equation. That's the world. So this is the most falsifiable theory ever invented. All you have to do is either find variables other than the wave function or find the wave function doing something other than obeying the Schrodinger equation. And there are ongoing experiments to do exactly these things. Karl Popper himself was a huge fan of the Everett interpretation. He thought that the Copenhagen interpretation was a philosophical monstrosity. So in terms of testability, Everett is just as good as anyone else's interpretation of quantum mechanics. Now, so those are, I think, the easily answered objections. There are two other questions that are harder. I'm going to just do like 1 minute on one of them and then a couple minutes on the other one. The first hard question is, where does probability come from? So as an empirical matter, when we do measurements on quantum systems, it is certainly true that the best we can do is to predict the probability of certain measurement outcomes. And in Copenhagen, that's because we put in a postulate into the theory that says there's a probability rule, okay? Everett, all the postulates are there's a wave function that obeys the Schrodinger equation. There's no mention of probability. In fact, the Schrodinger equation is 100% deterministic. If I know the wave function at one moment of time, I can predict it at any other moment. There's nothing probabilistic about the dynamics. So how in the world does probability enter what we know about quantum mechanics from experience? The answer is this idea of self-locating uncertainty. You can indeed know everything there is to know about the wave function, and there's still something you don't know, which is where you are within the wave function. So let's go back to the cat and the observer after decoherence happened, but before the observer knows what branch of the wave function they're on. Decoherence happens really, really fast. Typical timescales are less than 10 to the minus 20 seconds in a big macroscopic system that you're not trying to protect. So before the observer opens the box, decoherence has happened and the wave function has branched. So there's already two branches of the wave function, the cat awake branch and the cat asleep branch. But because the observer hasn't looked, there are two copies of the observer that are exactly identical with each other. Because the observer has not opened the box, if you ask the observer which branch are you on, cat awake or cat asleep, they don't know. They're identical. So even though they know the entire wave function of the universe, they don't know which branch they're on. That is self-locating uncertainty. And you can ask, given some reasonable assumptions, is there a uniquely rational way to assign credences, probabilities to being on one branch or the other. And you go through the math, and the answer is yes, and guess what? It's exactly the same as the postulate that you had in the Copenhagen interpretation. The probability is given by the wave function squared. So it is very natural for probability to arise, even though the underlying dynamics are completely deterministic. Now, the harder question is, how do we relate Everettian quantum mechanics to the world of the classical world we see of tables and chairs? And this is a tough one for me to get across because most of my fellow physicists don't even think this is a problem. I think it's the hardest problem, and we should all be thinking about it. But, we all grow up tending to think about the world classically. So we look around, we see there are cats, there are trees, there are people. Those are the starting point when we try to describe the world. So when even professional physicists make quantum mechanical models of reality of, spins or materials or particles, they start with some classical description and then they quantize it. So you start with some classical stuff, and then there's rules that you're taught in graduate school or undergraduate education for turning that into a good quantum theory. And at the end of the day, you have a wave function, which mathematically is a vector living in Hilbert space, living in this giant dimensional vector space. Presumably, that's cheating. Presumably, nature doesn't start with a classical theory and quantize it. Nature has no need for that. Nature just is quantum mechanical from the start, right? So in some sense, you should be starting with a wave function thought of as a vector in some abstract Hilbert space and deriving the rest of the world. This is how nature actually works. That turns out to be really, really hard, and it's harder in many worlds than it is in other approaches to quantum mechanics. In other approaches to quantum mechanics, whether it's Copenhagen or hidden variables or whatever, they sneak in some features of the classical world into the definition of the theory. Despite the fact that there are many worlds, when it comes to assumptions, when it comes to pieces of the theory itself, Everett is the leanest and meanest. Wave functions in the Schrodinger equation, and that's it. Every other approach to quantum mechanics adds extra stuff, and that extra stuff gives you a handle on why the world looks classical in a certain way. In Everett, you have to work harder. Why does the world look classical at all is a perfectly good question. So keep that question in mind. Why does the world look classical at all? There's another question that we have, which is quantum gravity. Right? I'm sure that you might have heard, depending on which street corners you hang out on, that we don't yet have a good quantum theory of gravity itself. We can take this procedure I mentioned over here, and it works for every force of nature and every piece of matter in nature other than gravity. For electromagnetism, the nuclear forces, particles that we know about, leptons and quarks and so forth, you start with a classical theory, you quantize it, you get a reasonable answer. For gravity, the best classical theory we have is Einstein's general theory of relativity. And his point is that gravity is a feature of space-time itself. Namely, it is the curvature of space-time. Space-time curves and warps in response to matter and energy. And we experience that curvature as the force of gravity. So he has a perfectly good classical theory. We can put it into our black box and we can quantize it, and we get a terrible mess. It doesn't work. We have not yet successfully taken classical general relativity and applied the usual rules of quantization in a successful way. That's why people are driven to consider alternatives like string theory or loop quantum gravity, etc. Those have made some progress, but none of them is obviously the right answer in any sense. So let me suggest the following thing, that maybe these two problems cancel each other out. The problem being we don't understand quantum mechanics and we don't understand quantum gravity. Well, why in the world should we understand quantum gravity if we don't even understand quantum mechanics, right? Maybe this fact that in Everett, you should start from a quantum wave function and emerge out of it, the classical world, is really the right way to think about gravity. In other words, don't quantize gravity in the sense of starting with some classical model and turning it into a quantum theory. Start with some quantum field theory and quantum theory and finding gravity within it. Well, we're allowed to take clues from the world as we do know it, where quantum field theory is the best way we have of thinking about particles and forces, right? If it weren't for gravity, Quantum field theory is the way nature works. So here's a picture of a field. This is the magnetic field, okay? If you have a magnet, there's an invisible force field around it. We know that because you put the magnet near your refrigerator and it reaches out and grabs it. Likewise, there's a gravitational field, an electric field, etc. In modern physics, everything is fields. So even particles, even matter, like electrons and quarks and neutrinos, there are fields that fill all of space, and what you perceive as a particle is really a vibration in that field. So the fundamental ingredients of nature, according to modern physics, are fields filling space, vibrating in certain ways in a quantum mechanical framework, the whole thing we call quantum field theory. And there's an immediate consequence of that, which is that empty space is fun. It's full and lively, and it's a busy place, okay? If the world were made of particles, you can imagine there are particles, and the space in between them is just space. It's just sitting there and nothing is happening. If the world is made of fields, fields fill all of space. And even where you say space is empty, there's nothing there, what you really mean is that there are fields there, but they're in their lowest energy state. They're in their vacuum state. And we can take space and subdivide it into little regions and talk about what the fields are doing in every region. What you mean by a particle is that the field is vibrating more than it does in its vacuum state, but in most of space, it's just sitting there quietly. And there's a feature that you can find in quantum field theory that different regions of space, the fields that are vibrating there, are entangled with each other. And the amount of entanglement is related to the distance between them, to the geometry of space itself. If two regions of space are nearby, they will be highly entangled. If they're far away, they're not very entangled. That is the conventional story of quantum field theory. Now let's ask ourselves, can we use this as a clue to find gravity, to emerge space itself? The point is we can't put space in, we have to find it in the wave function. So the suggestion is we can turn this idea around, the relationship between geometry and entanglement. Rather than saying when two parts of space are close together, they're highly entangled, we say when two quantum parts of Hilbert space are highly entangled, they are close together. That's what it means to be close together. And if you do that for all the different parts of the wave function, geometry emerges on space. And you cross your fingers if everything works out nicely. It's the kind of three-dimensional space that you and I know and love and live in. So we can easily imagine a relationship between geometry and entanglement. There is also a relationship between entanglement and energy. Remember, I said that in the vacuum, in empty space, there's a very specific entanglement structure in quantum field theory. If you want to put a particle somewhere, so you want to add some energy to a region of space by putting a particle there, you basically have to break the entanglement of that little vibrating quantum field with the rest of its surroundings. So you decrease the amount of entanglement in a region, and you necessarily add energy and vice versa. There's a direct correlation between the amount of entanglement somewhere and what we would traditionally refer to as the energy. So look what we got. By referring to entanglement rather than begging the question by assuming space and stuff like that, we find that there is a relationship between the geometry of emergent space and the amount of entanglement. There is separately a relationship between the energy and the amount of entanglement. Therefore, there's a relationship between the amount of geometry, the geometry of space, and the amount of energy in one region. But modulo some mathematical details that I encourage you to check out, but that's general relativity. That's what Einstein said. He said that the geometry of space is sourced by the amount of stuff, energy and matter, and so forth. What I'm saying here is that if you didn't know that there was any such thing as space, and you treated space as something that emerged naturally from the quantum mechanical entanglement between different parts of the wave function of the universe, the natural consequence would be that space has a geometry and it's curved, and that geometry obeys an equation that is very similar to Einstein's equation of general relativity. Now, we haven't proven this, truth in advertising. This is an ongoing research program that is not done yet. We've made progress, but the progress is the following. Rather than saying this is true, we have a long list of assumptions, and if all those assumptions are correct, then this is true. Okay, so it's full employment for graduate students in the future generations. They need to prove every one of our assumptions is true. But it's very encouraging to me to imagine that the problem with quantum gravity was just that we shouldn't be quantizing gravity at all. We should be taking quantum mechanics seriously and finding it. So I know that there's probably some details there that I went through too quickly. So happily, you can buy my book, which I think is free to you. I think you're giving it away, copies for free, but all the details are in there. The details that are not in there are referenced in there. It's an exciting time. I think that we're actually making progress for the first time in understanding how nature works, and taking reality seriously turns out to be a smart strategy for theoretical physicists. Thank you very much. We have time for questions.
Yes, we have some time. So does anyone have a question? Hi, look alive.
It seems very dangerous.
It's very soft.
We live on the edge here.
Okay, so Many Worlds Theory is the fodder for a lot of science fiction. Just off the top of your head, where does modern science fiction get it right, and where does it get it wrong?
Yeah, so that's a very good question. Modern science fiction almost always gets it wrong, for the following very good reason: that once the worlds branch, according to the real true theory of Everett, they can't talk to each other anymore. So you can download, if you have an iPhone, there is an app called Universe Splitter, where it will send a signal to a beam splitter that will send a photon either left or right. And if you agree ahead of time, if the photons go left, I'm going to have Chinese food for dinner. If the photon goes right, I'm going to have pizza for dinner. There will be a universe in which you had Chinese food for dinner and a universe in which you had pizza. But you can no longer talk to the other one and say, how was yours, right? So that does not make for very good drama when that happens. Now, there are, maybe the Schrodinger equation isn't quite right. Steven Weinberg, the famous physicist, suggested a modification of the Schrodinger equation. And Joe Polchinski, another famous physicist, pointed out that if that modification were true, it would enable communications between different branches of the wave function, which he called an Everett phone. So that's a perfectly respectable thing to write a TV show or movie about if that's what you want to do. It's crossed my mind, yeah.
If there's just a single wave function and the universe is just a ton of forking events that are creating all these different universes, I guess, is the implication then that there was ever or is ever just a single point or instance of entropy or like true probability or randomness that occurred?
Yeah, well, I think the way that I would put it is there's absolutely a direction of time in this picture, right? There were fewer separate branches of the wave function in the past than there are in the future. Now, there's separately an arrow of time given by statistical mechanics, given by entropy increasing. Entropy used to be low and is growing. I think it's the same thing. I think both cases are just facts that the initial conditions of our observable universe 14 billion years ago near the Big Bang were highly non-generic, were very special and very low entropy. And nobody knows why in either case. But whatever caused the wave function of the universe to have few branches and the physical thermodynamic entropy of the universe to be low explains everything since then.
So my question is related to this one. So if the branching needs to happen constantly, does that mean some sort of serialization needs to be done? Like
somewhat?
Serialization, like events needs to wait for each other before they can branch the wave. Like, how do you explain that?
Yeah, so I'm going to give you the correct answer, and it's going to be unsatisfying. Okay, let me make it concrete by thinking about the Higgs bosons and decaying and the EPR experiment, where Einstein said, look, I'm going to take particle 1 and particle 2, separate them by many light years, and observe particle 1, and you're telling me instantly particle 2 changes. You can prove a theorem that says that cannot be used for communication. You cannot send information that way because the observer at particle 2 doesn't know what the result was from particle 1. But following my philosophy that we want to understand what's really happening, you're still allowed to ask what's really happening, okay? So the answer is the wave function of the universe branches. What you want to know is, should I think of branching when I observe particle 1 as happening simultaneously throughout the whole universe? Or am I allowed to think of it as sort of spreading within the light cone of that particular point? The answer is either way. The answer is that the whole idea